I want to speak to a topic that is really a homegrown topic, but I think it helps to inform this group as we discuss climate change, because we got choices where there's the business as usual scenario, and then there's what are you going to do about it. Both of those have purposeful environmental consequences, and I wanted to advance this discussion to consider some of the possible environmental consequences. So I'm going to get into iron fertilization as an example, but I also wanted to hit on some others, other sequestration strategies that may be of interest, and certainly will be of interest in the fairly short term. So I was going to talk about the iron hypothesis, what the driving hypothesis is, and that is threefold. That iron deficiency limits phytoplankton growth, the little plants in the oceans, and therefore the uptake of carbon dioxide and the flux of carbon from the surface waters to the deep sea. This is the way the oceans mitigate atmospheric CO2 or play a role in the cycling of carbon. The secondary hypothesis that iron limitation is responsible for the persistence of what we know to be the HNLC, their high nitrate, low chlorophyll condition in the oceans. I'll talk a little bit about that. And then that iron supply, the third hypothesis, is that iron supply has limited or contributed to the interglacial drawdown of atmospheric CO2. Now, those were the driving hypotheses, and it has been tortured into the fourth, and that is that large-scale iron fertilization could be used to anthropogenically manipulate or geoengineer climate. And so I want to talk about all those, but it's too much to talk about, so I want to get to my conclusions right now. And that is this, that the nature of environmental science, many of which of us have been involved with, has enabled our understanding of many new aspects of paleoclimate and environmental forcing. Okay, number one, we're learning more about this all the time. I'm going to be talking about one example, the iron hypothesis. But there has been a striking transition in the way we think about this finding, and it was initially, to figure out how the world works, and it has been tortured and turned on its head to figure out how we can make the oceans work for us. And there's a fundamental difference in that, because it started out, the question used to be, how has iron supply influenced climate change in the past? To what will be the consequence of massive anthropogenic ocean fertilization in the future? And I think that's a question we need to be considering. The culmination of these processes now leave us with a planet that has been designed for one single organism. And one could suggest that that is the internal combustion engine, but it's actually modified, well, for a lot of organisms. Others of you might suggest that it's corn. But in fact, it's for anthropogenic purposes, as was demonstrated last month. And in the science paper that shows that over 41% of the oceans have now been strongly and negatively impacted by human activity. This has been our choice. And like it or not, what I'm suggesting is we're driving the bus. That is to say that human activity is now affecting climate. We're affecting the environment in such a way that we bear the responsibility of our futures, and it is our responsibility to know how to drive this bus and what the environmental consequences of our actions will be. It's particularly important now because carbon trading, carbon mitigation will become a $1 trillion annual industry, and this is going to produce tremendous international economic pressure to do things to the environment to get carbon out of the atmosphere and put it someplace where we don't know what, but it's our job to know that. This international pressure is being codified as we speak. So I'm going to talk a little bit about the costs of doing nothing. What are the costs of doing something? What actions should be considered, and what I want you to be thinking about is how to fill out the rest of this profile. What is it that we need to know in order to be able to responsibly engage in geoengineering or strategies? So, CO2 record. reconstructed here from tree rings, ice cores, and direct measurements indicate an unprecedented increase in CO2 over the last few years. This increasing CO2 represents a radiative forcing of around 2 watts per square meter. That's a lot. If one looks at the last 30 years, the greenhouse gases in composite contribute radiative forcing on the order of 2.5 watts per square meter. And 3 of these of the most important gases associated with this radiative forcing are biogenic and all involve aquatic systems. They're biological gases. They involve aquatic systems. Okay, that should speak to you as a marine scientist. Our revolution in the understanding of the carbon system, or carbon cycling, has recently come about with the discovery that iron plays a key role in forcing marine productivity and limits phytoplankton growth over great regions of the world's oceans. So now iron is tied to that 2.5 watts per square meter of radiative forcing. And so I want to tell you a little bit about how we discovered that iron was such a key element. Iron is critical for all life. You've got it in your hemoglobin. You've got it in your in a lot of enzymes throughout your body. Plants have it in ferredoxin, nitrate reductase, chlorophyll synthetase, nitrogenase. It's everywhere. And the genes that code for those enzymes are conserved over billions of years. So life on the planet evolved with iron in great abundance under reducing conditions. It was utilized as an electron acceptor, electron transport agent, and all life evolved with iron present until those nasty phytoplankton came along and started engaging in photosynthesis, which was around here where iron was abundant, and they polluted the atmosphere by splitting water and forming oxygen. And from about here on, the atmosphere has been oxidizing, and iron has precipitated in great formations and has been limiting phytoplankton abundance ever since. In spite of these extremely low concentrations of iron, all life forms still require it. This is a profile of, this is one of the first profiles of iron that was published. The analyst was Mike Gordon of Moss Landing Marine Labs, and one of the striking features of this profile is that it's depleted to sub-nanomolar levels, picomolar levels in the surface waters, and increases to sub-nanomolar levels at depth. Tiny concentrations to tiny concentrations, but it mimics the profile of nitrate, a plant nutrient. So, how much is that? How much is part per quadrillion of iron? Well, it's equivalent to a second in 32 million years, or a postage stamp on the area of Texas. That's the kind of concentration we're talking about. And so it speaks to 2 things. It's a pain in the ass being a phytoplankton in a region that's iron starved, because it's very difficult to meet your iron requirement for growth. It's also a pain in the ass if you're an analyst and trying to measure iron in seawater. It was quite a feat for Mike Gordon to get some of those first measurements. Now let me talk a little bit about the iron plankton requirement. This is the stoichiometry of life. This is the Redfield equation that represents carbon dioxide, nitrate, phosphate, water going to form carbohydrate and biomass here with the evolution of oxygen gas. It takes 1 iron atom to run this reaction 100,000 times to the right. Okay, incredible leverage for that element. Okay, so and it's cheap. That's going to come into play here pretty soon. The lack of iron supply to these regions of the world's oceans is thought to result from a lack of phytoplankton ability to grow and draw down nitrate. Thus, the lack of iron is thought to explain these HN, high nitrate, low chlorophyll environments. Okay? Lack of iron. So what happens if you put iron here, and could you get something to grow? If amended with iron, the planet would move more carbon from the atmosphere to the deep sea. That's the idea. And what are those budgets? If you take a look at the reservoirs, and this is what I call a shameful oversimplification, these are the reservoirs. Atmosphere, 700 gigatons of carbon. Ocean, 38,000 gigatons of carbon. Okay? Let's just consider those two reservoirs for the moment. Tiny changes in the fluxes between those reservoirs could have massive consequences to the concentration in the atmosphere. Okay? And how does carbon move? Carbon moves through the oceans in a manner described by the biological pump. And this is from Penny Chisholm's diagram indicating CO2 absorbing into the water, phytoplankton take up carbon dioxide, fix it into biomass. Some of that carbon is respired back into the atmosphere. Some of it is transported to depth and remineralized or respired. A small fraction is actually transported and sequestered on the seafloor. Okay? But it is the efficiency of this pump that determines how quickly carbon moves from the atmosphere to the deep sea. And if you recall, the deep sea can sequester carbon on the order of 1,000 years, depending on how deep that carbon is transported and at what depth it might be remineralized. But deep sea residence times on the order of 1,000 years. And there is evidence to suggest that this biological pump varied in the past. And here's an ice core record indicating high CO2, low iron, low CO2, and vice versa 3 separate times throughout the recent paleo history. Okay? So we have an inverse correlation between iron supply and atmospheric CO2. Which would suggest that iron supply is making something grow, making carbon come out of the atmosphere, and this is supported by the isotopic composition of non-sea salt aerosols. High iron supply, high marine productivity, low iron supply, low marine productivity. The integrating feature is this, that iron is swept off continents and drops into the ocean after being acted upon by the marine sulfur cycle. So phytoplankton produce organic sulfur compounds that come into the atmosphere, oxidize to sulfuric acid, dissolve atmospheric particles, and deliver soluble iron to the surface waters of the oceans. These are phytoplankton scavenging iron out of the atmosphere. So, I'm not kidding about this. So what we did was we tried some experiments where we added iron in that iron sulfate form to bottles from the Northeast Pacific. These are before iron enrichment and these are after iron enrichment. Very few phytoplankton, many phytoplankton. And in fact, this result became the topic of a series of papers. John Martin, glacial, interglacial CO2, the iron hypothesis. Carl Bonsa came back and says, does iron really limit phytoplankton production? These are the titles of these papers, by the way. Does iron really limit phytoplankton production in offshore subarctic waters? Martin writes back, yes it does. A reply to the comments of Bonsa. I published a paper on the effects of iron, manganese, copper, and zinc in the subarctic productivity. And then Bonsa says, now wait a second, rates of cell division in the field, and he had a comment relative to these two papers. And Martin wrote back again and said, we still say iron deficiency limits phytoplankton growth. Now, this is an amusing consequence, amusing sequence of publications and titles. But such disagreement between professionals rapidly drives the public to conclude that no one knows anything about this subject. They throw up their hands. And so we don't have much time. And we needed to conduct an experiment that was large enough to actually integrate all these processes. We went to the equatorial Pacific, got a great group of scientists from MBARI here, actually about 14 different institutions, threw a buoy over the side, put some iron in the ocean, This is pharmaceutical grade, by the way, iron sulfite, the type you'd take as a vitamin supplement, and found that we could grow huge quantities of phytoplankton where PCO2 dropped and phytoplankton photosynthesis increased dramatically. The ocean waters around the equatorial Pacific turned from what looked like blue to Monterey Bay green. I'll show you some pictures. The size class of the organisms went from little stuff to big stuff. And the biomass went up completely 400 or 500 fold. This is what your brain looks like without iron. This is what your brain looks like on iron. So this is really the difference between looking over the side in electric blue waters to green waters. We've subsequently repeated this experiment in the Southern Ocean on a series of experiments both north and south of the Antarctic polar front zone, both here and here. I'm going to skip over the data, but we got dramatic 40-fold increases in phytoplankton biomass in the north and over about a 300 square kilometer area, and another large patch in the south. So, you know, it has been published. There are subsequently about 15 other international experiments that have undertaken the study of iron supply to the oceans, and I am going to stop pretty soon. What I wanted to say that, and I'm just going to switch to the. So this is pretty conclusive experiments. People need to know what's going on here. There are some potential positive consequences of ocean fertilization. That is that pH, this reduces ocean acidification and it reduces atmospheric CO2. But there are lots of potential problems and unintended consequences with this technique. If you look at the price of climate change, it totals around $9 trillion annually by 2100. The cost of mitigation is around $1 trillion a year based on some wild geochemical assumptions. So what I'm suggesting, and I'll stop here, is that the price of mitigating atmospheric CO2 is less than the price of less than the price of damage control. And so if we're going to engage in damage control, we better be damn certain that we're not actually causing some other problem. And it's up to you guys to figure that out. I'll stop there.
Well, let's get started. I guess you've seen the title, so we can proceed from here. And I'd like to start with a little bit of background on sea level and sea level rise, maybe clear up one or two misconceptions. Start by talking about some of the factors that affect sea level and relative sea level and what we mean by relative sea level. Relative sea level is what we measure with a tide gauge, and it doesn't distinguish between actual changes in water level and movements of the platform on which the tide gauge is located. So of course that's a problem for working with tide gauge data. In any case, let's look at the factors now that contribute to relative sea level. The first four we can group together. They all deal with ice melt. The fifth entry here, thermal expansion, is a big ticket item, and we'll say more about that. Terrestrial storage is a very interesting one, and it's getting more attention now because it's thought that issues like extraction of groundwater, dams, reservoirs are actually contributing to maybe putting the brakes on the increase in sea level that we expect to see. It's not very well, the confidence in that, the uncertainty in terrestrial storage is quite large. Oceanographic processes, obviously we're going to talk about in just a minute. Isostatic effects deal with glacial rebound, and we call it GIA for short. Probably the worst problem we faced up until recently is local subsidence and uplift with tide gauge information. It's been a serious problem, but we now have something on the horizon. I think it's going to solve that problem. I'd like to say a few words about general circulation models, because this is a conventional way that we approach the prediction of sea level rise. And I emphasize that these are global circulation models because they do not predict sea level rise for any specific location. Issues related to GCMs. We have three different types, basically: atmospheric, oceanic, and then the coupled air-ocean GCMs. We call them AOGCMs. And they are extremely complex. They took years and years to develop them, get the feedback mechanisms worked out properly, and they only run on supercomputers. When these models are run, they're usually run about between 10 and 30 runs. What they do is they perturb the initial conditions slightly, and then they make another model run, and they look at the forecast trajectory. Now, the spread of the forecast trajectories gives an estimate of what the uncertainty in the forecast will be. Now, model uncertainties, this is an extremely short list, but the biggest ones deal with the emission scenarios for how we specify the greenhouse gas and aerosol increases over time. These are not outputs from the model, these are inputs to the model, and we have to specify those. And if we don't do it properly, then of course we're not going to get a good forecast from the model. Now, the coupling the feedback processes between the atmosphere and the ocean, of course, only applies to the AOGCMs, and they've got that pretty well worked out now. I'd like to give you a quote from a recent article in EOS, which is the AGU newsletter, from a modeler from NCAR. And I'll just read this off to you. Decadal prediction using GCMs still remains a frontier in climate science. And I emphasize the word decadal. And so I added the following, saying, so attempting to make forecasts over longer periods may lead to uncertainties that are unacceptable. So when I hear people talking about making a 100-year forecast, I really start to wonder. There are two approaches that are used with these models to make a regional forecast. One is nesting the AOGCMs, where we use a high-resolution model embedded in a global lower-resolution model. And of course, the nest is placed close to the area where we want to make the regional forecast. It's quite complicated, and I think they're working on that problem right now. I don't think it's been done for sea level rise, but it's been done for certain other parameters. The technique that's been more used is called downscaling, and this is a statistical approach where we used past data and use the global forecast from a GCM and try to tailor it to a given region using past data. Summarizing this, I would say thus there are really two major sources of uncertainty when we make a regional forecast using a GCM, and that is the uncertainty in the model forecast itself, and then there's the uncertainty associated with the downscaling process. And so overall, we're talking about serious uncertainties here in my view. Okay, here's some sea level projections. These are actually quite old. These go back to the early 2000s, and since then, the newer projections indicate much higher increases in sea level rise by 2100, and I think Dr. Samaro talked about this in his talk on climate change recently, that it might be as high as 1.4 meters. I think that's the figure you quoted.
Yeah, that's the state's report that came out in March this year.
Well, if we put that in terms like 4 to 5 feet, the implications are simply staggering. I mean, I'm not even thinking about California now. I'm thinking about places like the Gulf Coast states where the problems will be worse than they are for the state of California. But in any case, these are projections, and they give different results. Different models give different projections. And I would say that in the last few years, the spread in the projections has started to be reduced, which I think is a good sign. Okay, moving on. I'd like at this point to try to dispel a common myth about sea level rise, and that is that sea level rise will be roughly uniform around the globe. Some people have that misconception, and I'd like to clarify that. And I actually have a few sentences here from the latest IPCC report that deals with this very topic. And in this report it says, in agreement with climate models, satellite data and hydrographic observations show that sea level is not rising uniformly around the world. In some regions, rates are up to several times the global mean rise, while in other regions, sea level is falling. Substantial spatial variation in rates of sea level change is also inferred from hydrographic observations. Spatial variability of the rates of sea level rise is mostly due to non-uniform changes in temperature and salinity and related to changes in ocean circulation. So, with that introduction, this is a very ambitious figure that was based on an average from 16 AOGCMs from around the world. So you can imagine an awful lot went into creating this single figure. But the spatial patterns of sea level rise from these 16 different models from different countries around the world were used to create this one figure, which is in the latest IPCC report on sea level rise. And of course, what really catches your eye here is what's happening in the polar regions. We see this is actually the change in sea level between 2000 and 2100. So it's the expected change from these models over this next 100 years. And of course, the biggest increases are expected to occur in the Arctic, and that'll be due to changes in salinity. And in the Antarctic, we also see actually quite a significant reduction in sea level. And this is thought to be, this is not conclusive, but this is what the report says, it's thought to be due to changes in the wind field. But this is a result of a map that is an ensemble of 16 different model projections from these AOGCMs. Overall, the pattern shows that sea level rise will be different in different regions. Okay, I think we've covered that topic. Now for some of the oceanographic processes that affect sea level. And I'm not going to talk about all these, but I wish I had time to talk about the inverse barometer effect. Some of you are familiar with that. It turns out to be an issue for some records, and I'll show you that it's actually important for the record from San Francisco. The currents are obviously important. For us, coastal upwelling is very important. And coastal trap waves are transient, so I'm not concerned with them. Seasonal variability and the currents tie together because the currents are seasonal. And of course, low frequency atmospheric forcing deals with the wind field. And El Nino effects are particularly important. It turns out the sea level is very sensitive to El Nino warming episodes. Secular variability includes things like the Pacific Decadal Oscillation, and that's something we're going to talk more about. That turns out to be a big player. So here I'd like to talk about the record from San Francisco, and I'll introduce the first method of analysis that I have used. Actually, I've used two different methods. In some cases, they give very similar results, and in some cases, they don't. But the idea here is to isolate and identify the different atmospheric and oceanic processes that contribute to changes in sea level. That's the real goal here. I think you know where this is. It turns out that the tide gauge at San Francisco was installed in 1854 at Fort Point, which is underneath the southern end of the Golden Gate Bridge. In 1877, it was moved to Sausalito, and it remained there for 20 years. And then in 1897, it was moved back to its present location, which is this little building right here at the end of a pier at Crissy Field. In any case, what we have is a continuous record that starts in 1854 up to the present time. And it is one of the longest continuous records of sea level in the world. Here I want to point out the fact that we're all aware of the fact that the Pacific Rim, the west coast of North America, is tectonically active. And so it's been difficult to find platforms where tide gauge records are considered to be reliable for estimating sea level rise. And this table here simply shows all the locations that have been picked around the world in a number of studies that are considered reliable for estimating sea level rise. This is in a book called Sea Level Rise by Bruce Douglas and co-authors. But in any case, what I want to point out is this area right here. The only two locations along the entire west coast of North America that were considered reliable are San Francisco and San Diego. And so another reason why I've been spending a lot of time with the record from San Francisco. This is actually just a two-way layout of the data from San Francisco. It's actually been corrected for glacial isostatic adjustment, which for San Francisco is extremely small correction. And the inverse barometer effect, which I didn't write down here, but in any case, it's just been corrected for that also. But the point here is the fact we can't learn much from the raw data. When you look at sea level data from month to month, it varies tremendously. The few things we can see here is the fact that obviously over the length of record starting from 1854, that sea level is gradually increasing over time. And you can also see some seasonal effects here. You can see that sea level is lowest between about March and May. And you can also pick out some of the major El Niños. You can see the 82, 83, and you can see the 97, 98. But beyond that, there's not too much we can learn by looking at the raw data. Okay, I'm not going to dwell on the methodology specifically. We could get completely bogged down in that. It's called singular spectrum analysis. We just call it SSA for short. It's very much like the method of principal components, which most of you are familiar with. It's a method of decomposing a time series into a set of independent components or modes. And the number of modes that the data are decomposed into is determined by the user, and it's called the window length. As the window length increases, the modes become smoother and so forth, and so you lose resolution. Okay, moving on. This is the results of the decomposition using a window length of 132 months out of a total of 1,848 months for 154 years. And this shows the first 7 modes. The first mode I originally called the long-term trend. It accounts for about 40% of the total variance. The second mode is very interesting. We're going to set that aside. Modes 3 and 4 together correspond to the annual cycle and account for about 11% of the variance. Mode 5 is also interesting, and we set that aside. And mode 6 and 7 actually correspond to the first harmonic of the annual cycle. We call it the semi-annual cycle. So the way I approach this problem, and it's called sequential SSA, is to remove the big factors that you understand so that you can look at the residuals in greater detail. So what I've done here is to remove mode 1, modes 3 and 4, and modes 6 and 7, and then reanalyze the residuals to take a closer look at some of the other issues that we'd like to look at. Here is the problem that faces everyone when they start to look at this issue of sea level rise. Here I've shown the results for mode 1 using 5 different window lengths. And so, which window lengths do we pick to call a long-term trend? Whenever you get into this problem of estimating sea level rise, at some point the problem becomes subjective. You have to make a subjective decision. If you use smoothing techniques, you have to decide how much smoothing you're going to apply. So it will become subjective at some point. We're going to focus on this area right up here in just a minute. That's of considerable interest, at least to me, hopefully to you also. We'll see. Here is my effort in trying to actually extract a Pacific decadal oscillation. This corresponds to timescales that are interdecadal with a period on the order of 25 to 50 years. And what I've done here, the red trace is actually the PDO index, which is based on sea surface temperature over the North Pacific. The blue trace corresponds to 2 modes, 2 adjacent modes from my sea level decomposition. Now, at this point, I think phase relationship may not be meaningful, but I think the patterns are meaningful, and I think you'll see that there's a very strong resemblance between these 2 patterns. And so I think we have captured at least some of the variability associated with the Pacific decadal oscillation. I also want to draw your attention to the index and see how it turns down here around 1995, a very sharp downturn. I believe that's very significant for sea level today. Now here's where we get into what I consider pay dirt. This mode right here is the original long-term trend, the first mode. Now when we add to that the leading mode of the Pacific decadal oscillation, we get this pattern up here. And so now we've been able to show which of the modes are contributing to a change in sea level at the present time. From about the mid-1990s, we see that sea level is actually going down. And to support this, let me show you the next slide, which is one of my favorites. This is from the latest IPCC report. And this is based on satellite altimeter data from the period from 1993 to 2003. And this shows the change in the rates of sea level rise and fall over the Pacific Basin. And so you see the spatial patterns here now. And look what we see along the west coast of North America, particularly the US and Mexico. We see sea level declining at rates that may be at least 6 millimeters per year, while when we look over here in the Western Pacific, we see rates of increase that approach 6 to 9 millimeters per year. And one of the questions my colleagues and I are asking at this point, are they related? Is there a connection between what's going on in the Eastern Pacific and the Western Pacific? We know the scales are large for variability in sea level. Are they that large? And that's one of the questions we're now looking at very carefully. Okay, let's look at the results from another method of decomposition called empirical mode decomposition. This is relatively new, and I'm very excited about this particular technique. And it's an empirical method for analyzing non-stationary and non-linear time series. There are two components to it. The only component that we're concerned about here is what's called empirical mode decomposition. And although it's similar to SSA in the fact that it performs a modal decomposition, the mathematical basis is completely different. There's no connection whatsoever. But the point that I really want to focus on is the last one, and that is, unlike other methods of analysis, in EMD, the number of modes is determined by the data and not the user. And I think this is very significant because this makes the process one step closer to being objective. And I think for estimating sea level rise, that's crucial. Okay, here's the modal decomposition using EMD. The top panel is actually the raw, actually the original data. You can see the variability from month to month. It's tremendous. And the first three modes, really a very high frequency variability, which we're not really concerned about. Once we get up to mode 4, we start to take some interest. Now we're looking at annual time scales. When we look at mode 5, we're looking at interannual time scales, so that captures all the El Nino variability, ENSO variability. Modes 6 and 7 are particularly interesting, and we recently discovered, I wish I had time to talk about this, that this captures what is called the 10 to 15 year ENSO modulation cycle, which there's been a lot of interest in over the last 5 or 10 years. And those two modes together really relate to that particular time scale. Mode 8 is one that is interdecadal, and that again includes the Pacific Decadal Oscillation, but is not necessarily limited to the Pacific Decadal Oscillation. Modes 9 and 10 are particularly exciting to me because we were not able to make this decomposition using singular spectrum analysis. They were combined together, giving the mode that we saw, and that I called mode 1 from our SSA decomposition. Here we see that they actually can be subdivided, and we see here an oscillation with a period of 105 years. So the question that we asked was, is this an artifact of the analysis technique, or is this something that can be interpreted physically? And that's what we're really working on right now, but we'll get to that in just a minute. But down here is a long-term trend. It's an exponential increase, and we'll talk about that actually right now. And in a recent paper that came out in a timely fashion, because we've been looking for a working definition for what a long-term trend really is, and there hasn't been one in any of the textbooks that I'm familiar with. But the definition for trend given by Wu and Wang and several others in a recent paper is the fact that the long-term trend is monotonic, or a function that has at most one extreme value. So with that definition, it means that mode 9 does not qualify because that had two extreme values. It was an oscillation. So only mode 10 qualifies using that definition. And you can also see that the inverse barometer correction has had an impact here. In fact, it's the solid curve. After the correction is applied, we see the solid black curve. It's actually reduced the slope by 15%. So I would say that anybody who does not include that correction does it at their peril. In any case, the form of this long-term trend is exponential, and it provides a basis for projecting the underlying trend out to periods which are well beyond the present time. Okay, now let's look what happens when we combine modes 9 and 10. 9, of course, is this 105-year oscillation. 10 is the long-term exponential trend. We add the two together, and look what happens right up here. We see this rounding effect that I've been noticing ever since I started looking at this data. What's going on since about 1980? Why is the rate of increase in sea level decreasing since about 1980? And I came up with several half-baked explanations, none of which were really satisfactory. But now I think we can see at a glance. If we understand what mode 9 is all about, we can tell it mode 9 plus mode 10 give us this result. So this really, the inclusion of mode 9 explains what's happening in the last 30 years of sea level. So of course the real question is, what is mode 9 all about? And what I've done here is to take mode 9 and superpose it on the sunspot record, the 11-year sunspot cycle. And then I've smoothed the sunspot cycle slightly. And when you see the smooth version, you can see actually there's a little similarity between the 105-year oscillation and sea level and a smoothed version of the sunspot cycle. Now, this doesn't say cause and effect. This is just perhaps a good correlation. But down below, we've carried this comparison one step further. We did a empirical mode decomposition of the sunspot record. And modes 9 and 10 together give us the red curve here compared with mode 9 from the sea level decomposition. Now, I think all of you would agree that that's a pretty high correlation. There's a phase lag. That's not surprising, but the patterns are extremely similar. And so we are tempted strongly to look for cause and effect relationship here. And my colleague, Dr. Alexander Ruzmakin from Jet Propulsion Laboratory, has worked on solar activity for some time. And he says it's due to something called the Northern Hemisphere annular mode. And I wish we had time to talk more about this, but that's a whole subject in itself. So let's not go there right now. But in any case, we think we have a physical explanation for this. Okay, now let's go back to what we did before with single spectrum analysis. We now bring in we have modes 9 and 10. Now we bring in mode 8, which is the interdecadal band, which, like I say, includes the Pacific decadal oscillation. And look what happens when we add in mode 8. See, from 1995 on, see the sudden drop in sea level? It corresponds very closely with what's going on with the Pacific decadal oscillation index, very close. So I think we may have cause and effect here as well. Okay, we're getting close to the end here. New developments forecasting sea level rise and policy issues. This is very exciting. I remember at the very beginning I talked about the problems with subsidence and uplift with tide gauge data. In just the this is only about 2 months old, this paper just came out in GRL, where some folks from Europe, and we're in touch with these people, they've deployed GPS receivers on about a dozen tide gauges around the world. And they've got a record now which is 10 years long. And so, of course, it measures vertical displacement. And so with that, they can actually correct tide gauge records for any motion of the platform itself. And so to save time, I want to go to one particular record. We have 3 columns here. The first column is the original sea level data from various locations around the world. The center is for GIA-corrected data, which I won't go into. We're not concerned about. But let's look at the GPS-corrected data compared to the original data. And the one record I really want to draw your attention to, because it's so profound, is this one down here, which is Neah Bay, Washington. They've been collecting sea level data from the tide gauge since the 1940s. And you can see the trend here is very, very negative slope. And this record has never been trusted to use for estimating sea level rise, because actually it shows that sea level is decreasing at that location. And it's quite obvious that tectonic effects are responsible. So when we look at over here for the GPS corrected version, look what happens to the slope. It's now positive. And I looked at that with some detail, and actually the slope from this GPS corrected version of that data is very much like the record from San Francisco between about 1940 and 1980. So I think this holds new promise that really changes the playing field for using tide gauge data around the world. We're just about finished here. Forecasting sea level rise. We have the techniques now. We have the software essentially to do forecasting with singular spectrum analysis. We're in touch with 3 Russian mathematicians who published a book on singular spectrum analysis. You've probably seen it. It came out in 2001. But they spend a lot of time on forecasting sea level, or not sea level, but whatever you may want to forecast using singular spectrum analysis. And we're in touch with the lead author, and she's been very, very cooperative. And we now have the software that she has developed over a 10-year period with her colleagues to do an awful lot with singular spectrum analysis that we've not been able to do ourselves, and forecasting is one of those. We want to get into forecasting using empirical mode decomposition as well, and we'll work on that. But this is actually where we're at this time. We have the software, we're using it, we're experimenting with it, and we're starting to make experimental forecasts with it. So this is where we're at, And we'll use the same approach that they use with GCMs, and that is you start with historical data, and you make hindcasts, and you work your way up to the present time and see how well you do. We can do the same thing with empirical models as we do with GCMs, and so that's the approach we'll use. But that's where we're at, and let's a few parting comments here. Isolating and identifying the relevant oceanic and atmospheric processes that affect sea level locally may provide the basis for making empirically based forecasts out to periods that approach the timescales of the processes involved. The empirical approach could dovetail well with GCM-based forecasts by providing a running start or guidance over the period of the empirical forecast. So I don't look at GCMs and what we're talking about as being at odds with each other. They're actually complementary. There's moves in the direction of using empirical methods in other parts of the climate community. And I just read a paper from GRL that just came out 2 weeks ago, and they're using it now to forecast surface air temperature out to a decade, and it shows it looks like it's a very promising method. It's not the same as what we're doing, but it's empirically based. Let me go to the final thing here. So far, we've been unfunded in this work, and I think one of the big, appeals for what we're doing is the fact that it's really a low-budget effort that we're involved in. And compared to what it costs to run these GCMs, the cost of these time on a supercomputer, as you can guess, is quite expensive. And so running the GCMs is really a big deal. But what we're doing here can be done on a much smaller budget, and we're looking for a sponsor. I might also point out that the method that we're talking about here is we get an understanding of what's going on in the ocean. We get an understanding of the processes that are affecting sea level. With a GCM, you have a big black box and you get a forecast, but you don't gain any understanding from the forecast. You just get a result. Here we're actually digging into the data, we're dissecting the data, and we're actually gaining understanding as to what's going on. And I think that's really a very strong argument in its favor. And to wind up, policy issues. And this is obviously an extremely short list, but it's a starting point. And one of the things that's always bothered me is there's been so much effort given to mitigation, but you know, in a sense, to me, it's almost like getting the cart before the horse. Until you have some idea about what sea level rise is going to actually look like, why do you worry about measures for mitigation until you have some understanding of what you might expect to happen? The other thing is, are GCMs really needed to get started? I think I've already answered that question, at least in my view. I think the answer is no. And finally, this is something that is obviously a policy issue, and that is because all U.S. coastal states will be affected by sea level rise, shouldn't any effort to make forecasts be coordinated at the national level? Because, of course, we're here in California, but what about the Gulf Coast states and the east coast of the U.S.? Everybody's going to be affected that has coastal exposure. So I think that's a good point to stop right now. Thank you.
So I'm a scientist that's now working in science education, and from the talks and the papers that I read, I know that none of you are paying attention anymore at this point, because the adult person pays attention for about 15 or 20 minutes when they're being spoken to, and then their brains just shut down. So in an attempt to get something across to you at this very end, since I've got the kiss of death spot tonight, everybody's going to have to stand up and take a couple deep breaths. So if you just stand up, get some oxygen going to your brain, move away from other people, bring your arms up, take a deep breath in, and your arms down. Take a deep breath out. Now this time when you come up, open the chest, drop the shoulders, breathe in, and then curve and breathe out. And one last time, breathe in, and breathe out. Okay, and you can sit down. Thank you. You need that oxygen hit. All right, and I just won't do my last slide because I know I took the time out for that one. So I want to tell you about how I got into science education quickly, what life is like in science education from coming from a field in science. I'm going to then tell you about some of the trends that are happening in science education. The reason why I really wanted to talk to you today is because when I went to the last Marine talk, one of the things that came up is, what do you do if you don't have a science literate public? And I'm going to talk to you about what we're doing about science literacy in this country, the trends that we see, what the policymakers care about, and then I'll finish and talk to you about what's happening specifically in climate change education. Okay? So my path I came to California and I went to UC Davis. I studied zoology, and that was in 1978 when I started. And Berkeley and UCLA were in the top 10 colleges. Of all the California schools, that was the only two that were in the top 10. And California schools were in the top 5. Okay? So I came back to California in 98, 20 years later, and became research faculty here at Moss Landing Marine Labs, and the California schools were 46th. Okay? And I also came with young children who were just about to start school. And so I became really passionate about this. So what I found is the difference between science and science ed is that in science you have controlled experiments. You have a prevailing model or a theory for most things that people are working on. You refine that over time. And that there is somewhat of a disconnect, but the disconnect is between basic and applied research and policy. So there's some disconnect there, and I see that. What I want to tell you is that in science education, that disconnect seems a lot broader. There are people who are doing basic research on learning and the mind and how people learn and the different learning styles. That is not really getting to policy, and that's not getting into the classroom. Okay, so there's a larger disconnect that I see in science education. Plus, you're working with the human society, right? So it's really difficult to control. You've got different home situations. You've got different social norms. You've got popular trends and popular culture. And so once you get into the classroom, it's really hard to do controlled experiments. There's also logistics and costs. I mean, we want to educate the most people for the least amount of money, right? So we don't want to do it the best way. We want to do it the most people for the least amount of money. And then we want assessments. So we want to show that what we're doing really gets you results. And assessments, again, are difficult because it takes time, and it takes, assessments take time, and there's privacy issues. So a lot of times you want to see how kids do when you teach them something in middle school, what careers they choose. Okay? Well, and then your grant is for 2 years, or 1 year, or 3 years. And so you got to assess in 1 year whether 10 years down the line this kid's going to go into a science or technology field. And there's also privacy issues, getting access to grades and things like that, tracking people, without being a stalker and things like that. Policymakers really want numbers. Okay, when I actually talk to policymakers in Washington, D.C., they want to know, does this have an effect? What are the numbers? Show me the numbers. Okay? So those numbers are hard to get, and that's what they care about. So here's some numbers. Test scores, science test scores. One of the big numbers that policymakers look at. These are test scores at a national level. The places where we test science, which is in 4th grade, 8th grade, and 12th grade. And what you find since 96 is that we're getting a little better in 4th grade, and by 12th grade, we're actually getting worse. Okay? And in 8th grade, we're staying the same. If you look at it at a state-by-state level, then you look at what states have improved from 2000 to 2005, and the green states have improved, and California is a green state. Yay! We're still 46th. We're still 46th in 2005. So we've improved, but it didn't move us anywhere in the scale. It's not about the money. You might think it's about the money. We don't spend as much. We don't do as well. It's not about the money. The top 5 states that spend the most on education are shown here. And that's where they are on the scale. This is math scores. So it's all over the place. It's not about the money. Okay, so in addition to looking at California and being really sad about that, then you can also look at it nationally. And here are the United States. These are the TIM scores. These are Trends in International Math and Science Study. And what we find is that the United States is that white bar going across. The average is down below. So we're not close to the average, which is really good. But there's 7 other countries in this study that are significantly better than we are. And some of them are small. Some of them are like Singapore and Chinese Taipei and Korea, Hong Kong, Estonia, Hungary, and so forth. So, okay, so this is worrying the policymakers as well. How do we relate to other countries? Money doesn't matter in this case either. Here is Korea, and here's where Korea is on this scale. So they spend less, we spend a lot more. They're doing better than we are. The new TIM scores came out in 2007, and we haven't changed. If anything, we've gotten a little bit worse. And Singapore is the first one up there. They're actually getting better and better and better all the time. Okay, so in that time scale. Other things that don't always show up in the classroom is we spend a lot of time thinking about the achievement gap in this country. In this case, this is the achievement gap between whites and Hispanics. That achievement gap has been 25 to 30 on this scale for the last 30 years. And we are putting a lot of money into that and trying a lot of different things, and that doesn't move. One of the things that most significantly will tell you how well a student is going to do on these scores is how much education their parents have. Okay, so that's a really strong correlation. So it's not all what's happening in the classroom that's affecting these scores. But the bottom line from all these numbers is that we're not the best and we're not getting any better. That's the bottom line that the policymakers see. The other part of it is science and technology jobs are going up and up and up and up. Science and technology jobs pay 50% more than non-science and technology jobs. There are still grossly underrepresented minorities and women in these jobs, and 25% of the current US workers in these jobs are foreign-born. Okay, again, something that policymakers are really thinking about is that we're hiring, for our workforce, we're hiring from without. If you look at, these are undergraduate degrees in science and engineering. The United States is way behind a lot of other countries per capita. So we're not growing our own. Americans aren't pursuing science careers. Okay? What that means is that there's not the interest. So not only do we not have the knowledge and the content knowledge, and we don't also have the interest. Well, what builds interest in science careers? There's been studies done on all of these things. Some things are hands-on activities. Others are problem-solving and inquiry type activities, which are on the standards, but are not on the test. Okay, so just keep that in mind. Hands-on also science that we know about is not on the test, and funding for hands-on science has gone down. Career counseling. Math, science, technology, integration activities, especially in middle school. Most kids decide in middle school the 3 different careers of which they usually choose one, the majority of kids. So there's a lot of focus on career days in middle schools because that's when kids are thinking about what career they're going to go into. Mentoring, integration of career components into regular education, modeling of how this will work. How is this relevant to my life? Okay, a really important point. One of the first things when you want someone to learn something is you have to make it relevant to their life. And we know this from lots of work and lots of studies. Okay, so the relevance comes first, then there'll be buy-in for the understanding. Internships, summer programs, work experience. This is, I know, a lot more difficult because of legal issues when kids are minors, that going into workplaces and things like that. So that's really kind of deterring that. None of this is on the test, right? And remember, the test numbers are what policymakers are looking at. So more specifically, climate change education, since that's what I was supposed to talk about. Climate change education, there's a lot of it out there. There's a lot of agencies. There's the Education and the Environment Initiative and all these other agencies that have something to do with climate change. They have curriculum out there. That means the curriculum's there. Climate change education, if you Google it, you'll get their website. And they have a variety of curriculum, class topics, student projects that you can do in a variety of different fields. So climatechangeeducation.org. So there's a lot out there. There's actually quite a bit of funding. A lot of the major funding agencies, EPA and NASA, NSF, have climate change education grants. And there's also, the EE Link is another site that has a lot of environmental education, and they have a whole segment on different grants, little grants, and I mean it's pages and pages and pages long. And the nice thing, I'll tell you something, the nice thing about little grants is you can do things regionally, and I think that's really important, and I'll explain that to you in a second. The other thing is the California Science Standards. Those are the different standards for middle and high school in the different topics, and in parentheses are the number of standards that would fit under climate change out of the total number of standards. That might not be important to you, and there's also climate literacy standards already been developed in the classroom. Because if it doesn't teach the standards, it won't get into the classroom. Okay, that's the reality these days. Okay, everything is dependent on test, and funding is dependent on test scores. And if it doesn't teach to the test, it doesn't get in. Okay, and what I'm telling you is that climate change can get in. The reason, so let me just stop for a second and tell you what I think policymakers should know. One is that climate change education is a good way to teach science because it's relevant and it's current. And remember, I told you that's the important thing, is to get this into the classroom for kids to learn science in a relevant and current way. Okay? The other thing I would like policymakers to know is that regional programs can be very effective because they, again, affect those kids in that area to the topics that are relevant to them. And if you try to fund it to now go national, a lot of times it loses its effectiveness. And there are quite a few agencies like NSF that want it to, if it works regionally, they want to go national. Okay, and that's what the good news is about the small grants that are available in climate change education, because you can make regional changes. And I think those are the most effective. And the other thing that I want to tell policymakers is when you make an effort to increase test scores, you may inadvertently also decrease interest. Okay, and you're going to be shooting yourself in the foot when you want to get more people into science jobs. And then lastly, I just want to end with talking about the informed public. And this was a piece that was on NPR, I think when we were driving down at Thanksgiving, from November 4th. And I don't know if you guys heard it, but there was a researcher, Dr. Chapin, who is a history of science professor from Harvard University. And what he said is that 150 years ago, when Darwin published his work, most educated people understood that this was an important piece. Okay? Now, in present day, we have electronic media. We get so much science information out to the public all around the globe. And it's much more technical, much more complex, that even scientists from one field don't understand other fields that well in science and technology and engineering to make a judgment call. Is this a significant change? Is this significantly important? Is this good data? Right? So, you know, to tell the public to, well, look at the data and decide for yourself doesn't work for climate change and doesn't work for a lot of what's coming out of science. Okay? And what he concluded is that when people can't figure it out for themselves, they look to who they can trust and they follow what they tell them. Okay? And the people that they trust, unfortunately in this country, are not always scientists, and they're not always policymakers, and a lot of times they're talk show hosts. Okay? And that's where we're at right now. And I think the issue is not just educating the public, but getting the public to trust the scientists and the policymakers. Okay? Thank you.